Good evening, everybody. Can you hear me?
Good evening, Professor. Yes, you're audible.
Okay, thank you. Shall I share my screen first and I can start the session now? Okay, this today's sessions, we are going to learn about the wind energy. Then this wind energy is covering these following topics. I hope these all topics I already uploaded the model. Is covering wind measurements and sensing with some instrumentation also there as the wind energy conversions, global circulation models, and wind energy systems. Then one case study also we can discuss with respect to that wind energy, which is related to Sri Lankan situation. Before go to the measurement technique, shall we try to understand how these wind resources are? We obtain these wind resources. Actually, main energy source is the sun. The sun is the energy creator. We receive energy from the sun. Then we know the solar insolations in the different places is not equal due to the shape of our Earth. Then there are some temperature differences are there. Due to the temperature differences, generally the pressure variations we can observe here. Then there are the temperature variations throughout the world, especially the summer polar region as the equator region. Then generally that equator region we have the high temperature zones compared to the polar. With the polar regions with the low temperature, the air density is higher than with the temperature is high places is low density. Then some pressure gradients can be occurred. These pressure gradients we can occur here. You can see here now the pressure variations throughout the world. There is not only the temperature variation, maybe the geometrical spatial variations also we can observe here. For you know how, shall we try to understand how this air circulations throughout the world? Now you can see the pressure gradients are there. Now here those are the isobar lines. Those are the isobar lines we can observe. Some region may be low pressure, some region may be high pressure. Then there are the direction of pressure gradients are varying throughout the world. Now, what do you think about that? Now, the main driving force, that meaning of the driving force, main active force on air mass is the pressure gradient. Maybe some of the various forces may be acting on the air circulation. Then due to that modeling, we are developed the global circulations model. The first one thing. Shall I go for a small question from you as a motivation? My question is that, what do you think about air moves along with pressure gradient or air moves perpendicular to the pressure gradient? Then you should give this answer to my question. Shall I pass through one multimeter ULR? Please, I'll put into that into chat box. Please access that ULR. You can give your polls. Each and every student should give the polls to these two. This question is there. Is there? Then you can choose one option, the A or B. I think you can click on top of that the ULR. Then it can be maybe your mobile phone or maybe in your personal way on the computer. You can use that. Then think about that. Think about that. I hope we have some basic knowledge in the semester 1 also. Then actually we know the high pressure regions are there. Generally, you can see here, same as here. Shall I go to the previous slide? There are some high pressure regions are there, low pressure regions are there. The main driving force is the pressure gradient. Then what do you think about that? Then I hope each and every student need to be give pause for this case. I hope many students only 20, yes, only 30 students. Right. Shall I move? By the way, we will see the correct answer. Now, actually, I already explained that the what is wind here. The wind is a simple term, the movement of air throughout the world. There's energy, yes, there's an energy content because of the air has a mass there due to this velocity and mass, the kinetic energy is here. There is an energy content of the wind. The mass means obviously is a fluid flow, then there's a density, and there's a kinetic energy. We can we can use some technologies to absorb that kinetic energy. Yes, before that, shall we try to understand how the air movements are here? If the temperature is hot and cold there, then the simple single cell model, if you're going to develop a simple single cell model, then air should be always move to north to south. You can see here that there is north to south directions, and we select one circulation. We are calling this circulation. Actually, we are calling this circulation. You can see here there is circulation. Please wait. I'll take. Place a point. You can see. Actually, we are calling this a circulation. This is the name of the global circulation, the huge one cell. Then we need to develop a model to find out the global circulation model to maybe predict the wind potential and everything is there. However, then there is a temperature variations drive the force. However, you can see here, some other forces are acting on that. We are causing Coriolis force. The Coriolis force is the main hidden force, the force on top of the wind. Actually, the name of the Coriolis, the one scientist, he's basically sailor. Sailor in the Portugal, because of at that time, the most of the Portuguese is sailing throughout the world. Then they're using wind energy, wind force for their sailing. They use that. Then they need to find out the wind speed, wind variations, and wind directions need to be very much essential to find out their sailing routes. Then they try to understand that the pressure gradients are there. However, the pressure gradients is not only the force here, some other forces in acting on top of the core, on top of the wind mass. Then that's the point he addressed that. The name of that, the Coriolis force is the name of that scientist, that person. He is the trade wind map developer. The trade wind map developer, each and every month they have the trade wind map. By using that trade wind map, the sailors use what is their routing. as season also, because of they need to come from the Europe to the India, maybe, then they use they need to choose the routes as well as the season to the sale, come to India, as well as they need to find out the return path also. Actually, I'm not going to talk about very in detail of the vectors and these things. We can find out actually this the coreless force is due to the Earth rotations. We can see the Earth rotation is also one vector, as well as the wind direction is the one vector. Then two vector multiplications point is there, the sign, there's a cross product. That's the coreless force we can find out. Now, what is happening now is a high pressure and low pressure region. This is the main driving force, even though the main driving force is the wind, the pressure gradient, then the perpendicular to that, the coreless force is acting on top of that. You can see here, because of that vector product one. However, now the actual resulting path of the wind direction is not exactly from high pressure to low pressure. There's some other path. It may take some other parts. Actually, we are calling this a coreless force, and the pressure gradients, the resultant path is coming there. Then ultimately, actually what's happening is always the path is become the different path is not that is not in the place of here. That's like that actually. Then when we go for shall we think any moving particle is moving here, the perpendicular to that is coreless force is applied. That is coreless force. Then what happened? It is moving to that direction. Again, that is applied to this coreless force. The coreless force is always perpendicular to the wind. This again, that is come to the ultimate point. That is coreless force. This is due to the pressure gradient. So ultimately, this velocity, this is the ultimate velocity. This ultimate velocity is, shall we think, the ultimate velocity is balanced. That means it balanced to comply with pressure gradient force equal to coreless force. Now, what is happening ultimately? The wind is moving perpendicular to the pressure gradient. The wind is moving perpendicular to the pressure gradient due to that coreless force. Due to the coreless force. That's the phenomena they find out by the coreless force. Then actually, now the coreless force is acting in the northern hemisphere into this direction, then the southern hemisphere into that direction. Then you can see here, this is the angle of this latitude angle, this latitude angle. Then higher coreless force is applied maybe near the polar region. The lower coreless force is applied in the equator. General equator, there are some force maybe there, however, some amount of forces here. This is a very important point we need to find out here. Then I think now your answer, shall we? I hope now I already give the answer for you. Shall I show that this results? What is our results here? This wait, I am counting the results. I hope what you thought previously, now you need to think about that. Maybe yes. This is the results. What I need to show you here, the gradient. Yes. Okay, no problem. Now you can understand that that's the point here. What I need to teach you that what you had your previous thought, now you can need to change that because of maybe you will learn something in this point. Now, what is happening now? This is a global circulations model. Now now there are the three zones are happening because of the equator. It is moving there now. Due to the Coriolis force, it become again perpendicular to the surface. Again, this is the reason due to the Coriolis force, because the distance of these things, again, it can be divided by three zones. That's the reason there are the wind pattern of these three zones like that. This is general wind patterns. If there are no any geographical situation, there are no any oceans, there are no any landmass. However, there are some other changes may be due to the landmass as well as the oceans, roughness, mountains, and everything should be there. This is the model we can develop without any land effect, without any topological effect or the roughness of the ground. This is a global model, we can develop that. However, if we add to that the land properties, yes, we can show how the wind is the variation due to other things also. Now the wind, this is the way how the global circulation models are developed. We are calling those are the global circulations. Those are the global circulation. You can see here now here a little bit higher. Shall I move a little bit? You can gauge here. There's a height is a little bit high compared to the polar region. I know the temperature is high. Generally, the density of the air is low. Then the volume of air thickness in the equator a little bit higher than the polar region. It's very considerable amount. That we know that at the temperature of 25 degrees Celsius, generally it is 1.225 kilograms per cubic meter. Then is a polar region is smaller. Then like that type of situations. Then the thickness of air also varied. Now, these are the global atmosphere circulations. We are calling global atmosphere circulations. Then the wind is occurred due to that. This is the effect here. Ultimately, the solar energy is converted to the wind circulations. Then there's the wind patterns throughout the world is happening there, generally. Now, shall we think about that? Here. Those are I already explained that these are ideal wind generated pressure gradient and Coriolis force. The Coriolis force is the very important one. However, the actual one due to the landmass distribution. These also the vary due to some other effect with the hurricanes and everything are happening there. That also some other lot of variations are there. We need to add top of that the global circulations, these things. Then you can see here the real situations in the wind directions. You can see here, those are the satellite maps are there. Those are the isobars. I hope you know what you mean by isobars. That means the pressure, equal pressure lines. Those are the isobars. These are the wind directions. Generally, these are notations are there. There's a standard notations. It's give the direction here. This give the direction here. The number of lines there, it gives the speed. That mean strength of the wind speed. How much of the power of the wind speed. Now here you can see the all wind directions are aligned with isobars. All wind directions are aligned with isobars. Now, what is happening now? Then the wind is, if they're in low, shall we think? Then, if they're in low region is occurred here, shall we think here some low pressure regions? We think some low pressure regions are occurred here. Some low pressure regions, shall we some high pressure regions. Now, what happened? The wind is not blowing from high pressure to low pressure. Wind is not blowing from high pressure to low pressure. Then that's the reason cyclones are occur due to this Coriolis force. Otherwise, if the low pressure is occurred, quickly the high pressure wind is come to there, the low pressure can be cancelling out. Now, unfortunately, the wind cannot be moved into that low pressure region due to the coreless force. Then that's the reason these all these cyclones, hurricanes, typhoons, and everything is due to that coreless force. If there are no any coreless force in the world, if we need the quickly the low and high pressure is occurred, it quickly can be cancelling out. The low can be the wind mass can be moved from high pressure to low pressure. Then now you can understand that that's the reason. Then other important things that you can see here. Then this globe is here generally. Then this equator. Equator, if you do some band there, shall we think +5 and -5, we notice that in this region, there are very small amount of coreless force because of that sine, there's a sine angle, sine latitude angle is very small. That's the reason then in this band, very less amount of cyclones are happening there. Did you notice that any cyclones cannot be moved through the equator? Then if any cyclone come to the equator, because the coreless force is almost zero, all cyclones can be cancelling out. Did you notice that any cyclones is not go across through the equator? Then the Sri Lanka is located a little bit higher than the band +5. Hambantota also almost 6. Then that's the reason we also affected cyclones. Did you notice that all cyclones are moved towards the northern directions, may the Bengal Bay, always. That's the reason, because of that become a strengthen and strengthen due to that coreless force. Then actually we can explain that all this phenomena by using this effect. If the cyclone is moved to downside, that cyclone effect is weaker. However, the most of the time it can be also happening. However, if it is come towards the equator, almost it's going to be cancelling out. Yes, that is a very important point. What I need to address there. Some other point also there you can see here. This the high pressure is all the winds are always directed to the parallel with the isobars. Actually, I just before I took some satellite the animations. You can see then in the Sri Lankan situation, the present situations, you can see some the low pressure and high pressure regions are there. The wind is blowing always that direction. Shall I go to that slide quickly? That may be interested to you. You can see now in the present animations. You can see here we can change the level of that line. Shall we go to 10 meter height wind speeds are there in the present situation like that. All things are parallel with the isobars. Okay, shall we move forward? I have another video also. This little bit. This very small video I found in YouTube. Shall I share with you? Please.
So we're on the northern side of the equator.
My name's Huntington Kalunji doing the experiment.
There's the north of the equator.
So right now we're north of the equator.
So we're on the northern side of the equator.
My name's Huntington Kalunji doing the experiment.
There's the north of the equator.
So
Water's going down.
clockwise.
We're going clockwise, northern hemisphere.
Huntington Kalunji are my names, Equator Guide.
Yeah.
So we're gonna see the south and see whether to go the other way
Yeah.
around.
So we're going clockwise.
north, yeah. UK. From which country?
From Australia,
Australia. That's south of the equator.
Yes. but born in England.
Wow. Been in both hemispheres, eh?
Yeah. So northern hemisphere, water's done.
Okay.
All right, let's go. Across the south, into the south.
Actually, this equator,
They also have
fortunately, they can
stabilize.
across the equator in Africa. The one side is northern hemisphere, other side is southern hemisphere. The rotational direction.
It works.
is here.
Thank you. So we need to do the last one at the zero. What happens when you have the zero latitude?
What happens there?
There's no rotation, just goes straight up.
Boo.
Come and see.
Wow, let's go. This is on the equator line. So what is it called when you're standing on the equator? Where are we?
No, we are at the equator where you weigh 3% less. The body weight is less by 3%. Okay.
Oh my God, I am fully spun out. Come on, boss, what's the magic?
No much is next.
What's the magic, boss?
Coriolis effect.
There's a cordless force. You can see here, I think, I don't know about your wash basin one. There's a cordless force. Affected to the cordless force. These cyclones and each and every masses rotating. You can see in the northern hemisphere and southern hemisphere, it is not same. Actually, this is the one picture I found from the sea, from satellite. This is due to the earth. That's the earthquake. Can you remember the tsunami to Sri Lanka at that point? This is the at that point. There's the hot pot of that is Indonesia in December 2004. There's this location here, that is counterclockwise. That is counterclockwise. This one. Then as well as some other hurricanes in Katrina, that also I found out from the internet. That also counterclockwise, and that is in northern hemisphere. Then some other cyclones in the southern hemisphere, that is near the Cuba, I think so. Then that is clockwise. Then it can be noticed that there is always the cyclones are rotating in the southern hemisphere in the clockwise. The northern hemisphere is counterclockwise. That also due to Coriolis force. In the equator, there is no any cyclones are any hurricanes and everything. Yeah, that also one other tropical cyclones in the South Atlantic basin. That also clockwise. Now, that is the global circulations phenomena. I hope you can understand that. The temperature, the temperature is the main effect for the pressure gradient. Due to the pressure gradient, the wind is a driving force is due to pressure gradient. Then effect of the Coriolis force, these directions are varied. Due to this all weather situations, the climatic situation, and a lot of currents and everything, the monsoons and everything, due to these two effects, the pressure gradient as well as the Coriolis force, both are on top of that. This correlation is also very much important sometimes, not only for a wind. If you launch a ballistic missile, need to be considered correlation force, otherwise your aim is not corrected, as well as aircraft and everything, maybe trains and everything, this correlation force are affected. I don't know about your wash basin, then think about that. You always say wash basin is a water swells and going to drain that the same rotations, the same direction, the rotations, the anti-clockwise, because we are in the northern hemisphere, that also may be a correlation force. The same as that what we show that video, very small, the water bucket, we can observe very clearly direction of the movement of airflow. Yes. Now, shall we move to other topic, the wind measurements. Wind measurements. Yes, that also I would like to take some pause from you. I hope you have some idea about that, because of that's the reason why I give that type of questions for me, because semester one we learn up to something about the wind measuring instruments. Then point is here. There are three wind measuring equipments are there here. There are three wind measurements equipments are there. It's a cup and movement. I hope you already learned about that cup and movement. I hope you already seen this type of cup anemometer. A lot of places, maybe on the top of the buildings, maybe the wind measuring places, and many places. The ultrasonic anemometer also people can use there because of for wind measurements, and the proper type anemometer. Then my question is that what is a commonly used wind instrument for wind energy measurements? I'll put you to that ULR to the Moodle. Then please you can give the poll out of that. Actually, I asked that for wind energy measurements. Wind energy measurements. It's the wind energy measurements. Actually, people are using for weather measurement also sometime. Then actually, these type of things can be used for different applications. Those are most commonly applications are there. The cup anemometer may be the mostly commonly used in the world, because maybe there's the cost wise it is much cheaper. Ultrasonic little bit expensive due to some other sensors, as the ultrasonic generators should be there. And prototype also there in some places. Okay, by the way, you can give these polls. I hope you just all students need to give the polls to that three categories. Maybe you can guess that, then as well as by the way of your learning, you can compare with your previous knowledge and then learn a little bit more. Yes. There are some wind measurement equipments. The first one is the windsock. The windsock is there. This one is the windsock. This one is the windsock. Then here's the cup anemometer. Actually, this cup anemometer is always incorporated with the wind vane. Always. This ultrasonic one, as well as some remote sensing equipment also there. I'll discuss with you very soon. What are the things? Did you see this type of windsock before? Any places? Did you see? Did you see any?
Yes,
Hope you
mostly in
can,
airport.
The airports most of the time.
Airport, the most sign. What else? What else? Yes, obviously airport. mm, some manufacturing factories, sometime maybe petroleum, maybe because the firefighters need to be find out the wind directions. Then these places, the gas storage places, maybe some the fire hazard places. Also, people are using windsock. Yeah, the reason is that's the point here. These things can be used different applications. Shall we discuss this one first? This can be observed from long distance. Can be observed from long distance generally. That's the reason. Then yes. Then generally, then the windsocks are using for airport because of the pilot need to be find out the wind direction. Why? Because of the wind force is applied top of the aircraft, then the landing directions need to be find out because of the speed of the aircraft as well as the wind direction is both need to be considered resultant angle with the track, the pathway. Then he need to be find out the wind direction and speed both because of he has a speedometer in the inside the aircraft. Then he can observe that windsock. The number of bends are there. This is a standard instrument. This is the standard instrument. This is the bends. There are, I think so, the 4 bends are there, 5 bends are there. The where it's bends now, we can find out what's the speed out. You can see here the bend at that point, the wind speed is calibrated value. This is a real calibrated windsock. The people can find out what should be the wind speed there. The bend at that point, it is around 5.5 kilometers per hour. It is bend at the second bend, it is 11 kilometers per hour. Here is a bend at this point, it is 16, like that. Here is the 12, the 28 plus. Then this is the how the pilot can be understand that the wind speed at the ground level is the ground level wind speed, as well as the wind direction is obviously we can find out because of there is the direction towards the wind direction. There's the opposite to the wind directions. Yes, that can be very much useful instrument for the airport as well as for firefighters. The firefighters need wind speed as well as directions for firefighting, for maybe the oil storage places, the gas storage places. That's the reason. So some factories, the places that the flammable gases emit, this type of the windsocks are people are using there. These are the applications. Then please consider these things. Now, this cup anemometer. This is the cup anemometer. This cup anemometer is a very much the simple instruments, very much simple instruments. Where did you see this type of cup anemometer? Obviously, there's about the locomotive, the weather station. There are many cup anemometers. I hope you the travel beside that road, you can saw that. You can maybe seen that type of cup anemometers. There are many places. There's a cup anemometer. The concept of that cup anemometer, concept of this cup anemometer, there's a cup is there. Shall we think there are generally it used 3 type of cups there. There's a projection of here. The wind is coming here. There's a force is applied. There's a force is applied. Then it's rotate. That is rotate. Then the wind speed is here. Generally, if there are no any friction on top of that, shall we think from here to there, that is radius is r. That is r. Then this speed can be determined by the r omega. That is rotational speed. That is rotational speed. Now the wind speed is directly proportional to the rotational speed. This rotational speed we can measure. This rotational speed we can measure. Generally, this rotational speed can be measured by the different technologies. Now that the photo effect, that the light effect is used in there. Then there are some wheel is there, like that type of red type of wheel is there. Then is light is coming there. It's a number of pulses generating. Then there is a counter. There's a light pulse counter is there because of it need to be the frictionless method to take the measurement of RPM. There's a rotational speed. If it is generating any electric device, the magnetic one, it applies some resistant torque. Then this is very much accurate instrument. You can see here actually the measurement and output. This output measurement parameters. We need to take measurement of wind speed, but we can measure the rotational speed. Then it is directly proportional. Actually, this is the equation there. This is the equation here. Then this is very much accurate equipment we can use. This one. Now, what is the disadvantage of this type of equipment? What is the disadvantage of this type of equipment?
We
Then,
cannot measure the
sorry?
direction we cannot measure.
Yeah, the direction instrument, yes, then it need to be used some different instrument for take direction. Yes, that is correct. That's the point of wind vane. Different separately, we need to use wind vane there. That is correct. Another point I need to address with you, that is the mechanical instrument. There's a mechanical instrument. It has a mass here. That has a mass. Without the massless cup anemometer, we cannot be developed. It has a mass there. Then it's a rotating mass. Then if the rotating mass, what is happening here? It's a moment of inertia there. It's a moment of inertia there. It's a moment of inertia. Then if it is wind speed is varying, if the wind speed is varying, shall it in the wind speed is some varying very quickly. Some gust is there. Then this omega also need to vary. Now this acceleration is coming there. That is acceleration is coming there because the angular acceleration is coming there because of that this omega is varying. Now this is a torque. The torque is applied. This torque is generated. Now what is happening is due to that moment of inertia, that rotational speed cannot be quickly response with the wind speed variation. That means instantaneous variation of wind speed cannot be measured by cup anemometer. That's the biggest disadvantage sometimes. Then please keep in remember, if you want to measure gust, the quick variations, then because of already it has a moment of inertia. I hope you can you know that what is moment of inertia. Yeah. Then due to that moment of inertia, the omega is not comply with that wind speed variations. That's the reason. Please keep in remember these values generally for energy measurements values. The 10 minute login time we are maintaining most of the cases. That is given by the manufacturer. This 10 minutes login time is given by the manufacturer, the mass of that cup actually. A very light cup may be very, very light cup, even though very, very light cup also there is some amount of inertia. Then the 10 minutes may be little bit keeping very somewhat smaller value. But the standard value is a 10-minute variation. 10-minute variations we can capture by the cup anemometer. Then instantaneous variations we cannot be measured here. Then the cup anemometer, the advantage of the cup anemometer is here. The wind speed is directly proportional to the rotational speed. Then no any calibrations are no any nonlinear calibrations are not prepared for this type of instrument. Some other instruments it prepared nonlinear calibration because of the measurement and output maybe not directly proportional because of this is a very important one for measuring equipments. Then the biggest disadvantage is a moment of inertia. Now, that's the wind vane. I hope that's a wind vane is very simple concept here. Then the wind direction can be measured, obviously. The way the wind is coming there. That also the quick variations cannot be measured there because of The wind vane also has some moment of inertia. Then the quick variations cannot be find out here. Then think about that. Where we require the quick variations. If it's a large wind turbine, the quick gust wind speed, do we require the gust wind speed? Yes, sometime because of the dynamics. That maybe need to be estimate the wind gust for their that is dynamics, to find out the dynamics of that structural and everything. But for energy wise, but for energy wise is not much required. The energy wise, the 10 minutes login time is sufficient because of the wind rotor also have a lot of moment of inertia. Then that variation cannot be addressed here. Other one, ultrasonic one. This ultrasonic one is used Doppler effect. The Doppler effect. Do you know Doppler effect? Any student can be, please. Do you know Doppler effect? Doppler effect.
Observed frequency changes based on speed of the sound.
Yes.
That is
yes.
perceived.
Correct. We can notice that any ambulance coming towards us and an ambulance passing from us, that's Doppler effect we can clearly identify it. Then this ambulance siren, then it is coming sound is not equal, it's going away from us. That is not equal because of the sound is coming toward us. That frequency is becoming higher and higher because of compacting. There is compacting frequency because of the moving object also coming toward us, the sound also coming toward us. Just add to that the sound speed plus the moving object. Then if it is going in the past, the pass away, that is the minus way. Then the sound, there's a sound, ultrasound is here, the sound effect because of sound speed is not much high, it's not much higher value as a light. Then it's a Doppler. That means that sound Doppler effect we can very clearly understand that even though maybe a ambulance, maybe a train horns, like that type of things. Here also, it generates some ultrasound here. Then one is receiver there. Then generator receiver there. Then there is the phase shift of that the sound wave. It can be calculated wind speed here. Now, this advantage of this ultrasound anemometers. Now, the moment of inertia effect is no more there. The moment of inertia effect is no more there. These ultrasonic anemometers can be used in the instantaneous wind measurements, variations, that means quick measurements, that means gust wind variations. Then the quick variations can be find out here. As well as these ultrasound anemometers we can use for controlling applications. Sometimes the wind turbines may be required. Some wind turbine may be required the maximum power point tracking concept sometime because of the real time actual wind speed need to be measured. If you are using a cup anemometer, this is due to moment of inertia, it cannot be measured real time exact wind speed because of the variation wind speed. If the wind speed are varied with the variation, the instantaneous the wind speed cannot be measured by cup anemometer, but ultrasonic one, it can be measured because of there are no any moment of inertia. There are no any moving parts. Then as well as the other important one, the cup anemometer can be measured only horizontal wind speed. I hope you can understand because the cup is rotating. The axis, the vertical axis, it can be capture only horizontal component. Then it can be capture only horizontal component. Any vertical component cannot be measured by cup anemometer. But that ultrasonic anemometers can be measured 3D. That's the point. The 3D measurements can be found out here. There's 3D. Actually, 2D ultrasonic sensors also there. However, 3D, this technology can measure 3D component. Then obviously, if you're going to measure any wind speed, any places, yes, obviously there are the vertical component also sometimes due to that ground effect and everything. That point also there. It's the most common concept is Doppler effect. Keep in remember all those things what I explained here. The techniques is Doppler effect. The advantages are it can be measured instantaneous, variation of the wind speed, and as well as 3D. That means not only horizontal component, the vertical component also can be measured here. Then by the same instruments, it can be measured the variation of direction and speed both. That also another important one. Then here the disadvantage here, there are a lot of signal processing is required here. So that is not like the simple the correlation, the wind speed to RPM correlation we can observe in the cup anemometer. That not like here. There are a lot of calibrations. The accurate calibrations are required in these ultrasonic anemometers. Those are the another disadvantage, as well as little bit expensive. This is expensive equipment. Then those are the advantages and the disadvantage of each and every equipment we can use as application wise also. If somebody need to find out instantaneous wind speed for controlling applications, as well as maybe there need to be any dynamics find out places, then this ultrasonic controls application of the controlling, these ultrasonic anemometers are required. Yes, this remote, the remote sensing wind measurement also very much popular. So LiDAR and SODA is a two systems. So LiDAR is using the light. That also using Doppler effect. The SODA is using the sound wave. It's a light wave and sound wave. That's two concept is there. Then it can capture maybe the particles moving very uppermost atmosphere. Then there are two or three tracking points are there. That's a conical type. Then throughout that the cones, it can be find out the pathway these particles. Then it can be tracked and it can be measured the speed of these particles, maybe dust particles. So that can be captured like that. The important one is the remote sensing one. You know that for energy cases, actually for energy cases, we need to build a wind mast. Then the maintaining of wind mast is not simple. Simple is costly. The wind mast also maybe 100 meters. Because of wind turbines, the percent of the nowadays the modern wind turbines height almost 100 meters, 80 meters, 70 meters like that, but on 20 meters some cases. Then we need to build a very large, very high the wind mast here. It is expensive. Then how about this remote sensing one? Very simply, we can fix this type of LiDAR or SODA on top of the ground level. It can be take measurements. Even though these instruments also expensive, how we are calling remote sensing. That means remote sensing, meaning of remote sensing, the measuring point, we are not any probe there. We have not any probe or sensor there. You can see here the previous case, anemometer, the cup anemometer or ultrasonic anemometer. At that point, we are taking the measurement. But here, that instrument is located in far away, but the taking measurements little bit some other places. That's the point. The remote sensing wind measurements. Then actually, it's a LiDAR and SODA concept are only not using out of wind speed. Some other applications we are using here, maybe a particle dispersions technology because of the pollutions controlling sometime because of the pollutions, the particulate matter can be dispersed throughout the atmosphere. Then at that cases also we are using the LiDAR SODA for that type of measurements, the pollution monitoring cases. Also, we can use this technology. But in this point, we are focusing to wind energy, solar and LiDAR, the both technology we are using. If this application is remote sensing, very high level atmospheric wind speeds can be measured here. Maybe you can see here, actually this global circulation, we can observe that. In the lower level, the wind direction is some other way. The very higher level, it is other way around. Then sometimes you can see in the cloud moving some very clear day. In the lower level, if the cloud is moving to some other direction, very higher level cloud is moving to opposite direction. That's a general way. That's the reason we are calling the circulations things. The return and this return path. Coming and both are return path. Then a very higher level the direction we can measure by using LiDAR and soda, because of the wind mast cannot be go like that type of 2,000, 3,000 height. Other one. Those are the instruments, maybe hot wire anemometer. Some student maybe know about that hot wire anemometer. Actually, these type of instruments are not using for energy measurements in the lab equipment sometimes, because of very small. Actually, hot wire anemometers are using very small flow, very small flow. There's even though like this type of small flow can be measured here. Very small flow we can measure by hot wire anemometer. This is a hot wire anemometer. Where we require very small flow rate. Very small flow rate. The concept is here. There's a hot wire there. Then it can be calibrated by the wind speed and the temperature. The both. Then this hot wire is calibrated to the wind speed here. How the heat transfer to the airflow. Then there's a working principle. The high temperature to the low temperature heat transfer concept. These applications we can measure even the very small flow rate. This instrument is not suitable for high speed wind measurements. High speed wind measurements. This is not commonly used for very small measurements. Maybe airflow in a duct line and any lab equipment places, the drying and the process line sometime. Then these places we can use that hot wire anemometer. Then a handheld anemometer. Where did you see this type of one? Maybe people are using that HVAC people using, no? The HVAC people using this type of handheld anemometer. It is incorporated with temperature and humidity, wind speed, the both. There's a duct line, the temperature and everything. The one instrument can be measured here. There is a main disadvantage. It needs to be properly directed. So orientation is very much critical. Otherwise, the correct wind speed you cannot find out because of that. Because of it is a propeller type. Actually, we have also that there's a fan is there. The disadvantage is here, that is the propeller RPM is not directly proportional. It is some curve here because of this rotational speed is not directly proportional to the wind speed here. Then there's a curve there. They need to be calibrated properly. And that is not like cup anemometer because of that. Here there's an aerofoil. The shape of the aerofoil and everything is depend on the RPM and the wind speed. Then these things need to be calibrated. It's already calibrated one and need to be calibrated point to point. Then that is also different applications. The most of the cases, this type of instruments we are using indoor applications, not for energy applications. So pitot type anemometers also there because of the completeness. We need to find out this also the lab equipment. That also not using for a weather data or energy data. It is this equipment also used maybe inside a duct or the pipeline, any fluid flow. The other thing is the pitot type. The pitot tube is using aircraft. Most people, there's a small pitot tube in front of the aircraft. Then that pitot tube is used for the speed of that with respect to the air. With respect to the air, it gives the speed because of the with respect to the air. Then is a pitot tube is given there. When you fly in an aircraft, there are two speeds as given in the navigator system. One speed is relative to the air, other one is the ground speed. The ground speed is given by using GPS. That is different technology. This GPS is using for measurement for ground speed. The pitot tube is used for the wind speed. That means with respect to the aircraft moving with respect to the wind speed. This is a pitot tube concept is also can find out here. There's a pressure difference. By using the pressure difference, the pitot tube concept, the fluid dynamics concept is using here. Now, those are the basic equipments we are using for wind measurements. Now, my answer for this one. Actually, the most of the people already give that answer here. We can see here. Okay, can share out that students give a lot of yes. Actually, the cup anemometer is the most commonly used instrument for the wind energy measurements. Actually, we can discuss these things very clearly. Here, because of a cup anemometer is most user-friendly equipment, the more accurate equipment is used for a wind energy measurement. So 10 minutes login time is much more sufficient to take wind measurements. That's the reasons. Then the ultrasonic one also can be used, but due to that expensive and everything, people are not using there. The popular type one generally used for indoor applications. Is the case. Okay. Your answers would be cup anemometer, right? Do we have any questions you can raise in this point? No problem. Are there any questions regarding wind measuring equipments? Or shall I move forward a little bit? Okay. Yes, now shall we move to wind energy conversions, concept of wind energy conversions. Actually, this conversion technology very deeply we will learn in semester 3 all technical with all technical concept. Here in the semester 2, I'll give the basic level conversion principles. You already know with the knowledge of semester 1, the wind energy has some kinetic energy. It can be absorbed by wind rotor. Wind rotor can be converted wind energy to mechanical energy. Wind energy to mechanical energy. there are type of wind rotors are there, vertical axis or horizontal axis. The people are commonly use horizontal axis one. We will learn that why we are commonly using the horizontal axis one. Actually, the reason is that horizontal axis wind turbines are more efficient compared to the vertical axis one. The values are roughly there's a horizontal axis wind turbines in the conversion efficiency is almost 42%. That means 0.42% we can convert it to mechanical energy. But in the vertical axis one, there are two types of darius and so on. Yes, those are both type of little bit lower than maybe 26 maximum. There are a lot of advantages and disadvantages are there compared with horizontal axis and the vertical axis one. Shall we focus today horizontal axis one? If you have any questions, you can, no problem, you can arise any point. We can discuss in detail. Now, the main point here, we need to convert wind energy to electrical energy. That's the main idea. Actually, we can convert to mechanical energy directly any other places like the water pumping or the grinding fly and mechanical applications. But in the present day, people use the wind energy conversion to the electrical energy. Then the wind rotor is there again. Obviously, the gearbox. Some wind turbines has gearbox. Some maybe not need gearbox. The reason is that need to be comply with that rotor torque speed characteristics with the generator torque speed characteristics. Normally, generators may require higher rotational speed. Actually, the rotational speed of generators depend on number of poles inside there. There's a electrical concept. Then if we have the high number of poles, yes, obviously it can be generate energy bit low for rotational speed. Then if we are not using gearbox, we need to use multi-pole. That means high number of poles generators for directly coupled with the wind rotor. But in the commonly, because of the multi-pole one may be expensive sometime, then gearbox is also there. Then this is the concept here. Shall we a little bit talk about what are the aerodynamics here? Then it's the kinetic energy. One here, the kinetic energy always has mass and velocity. The mass is always density and volume here. Density is very important case in the wind energy. Then I think in the Sri Lankan situation, we are not much observe the density variation throughout the year. Because of we are not much observed, we are not much experience high temperature variations in our climate, maybe maximum 5-10 degrees. But some other countries is maybe observe very high temperature variance. Then here that is the mass. The mass is actually density into this volumetric flow rate. That's a volumetric flow rate. It is density is dependent on temperature. That's a function of temperature generally. That's the reason in some cold countries, it can generate more wind energy in winter season because of air is very thick. That the energy content, the kinetic energy content in the cold air has much more high energy compared to the hot air. That also one thing, yes, here that is a density point here. We are calling the swift area. Here there is a wind rotor. We are calling the swift area. The swift area is the captured energy from wind. That's the area. That is the diameter of the wind rotor. Then we are calling there's a swift area. Then the wind speed is coming there. That is coming here. Then what is happening if you use a wind rotor here? Here's the wind rotor is here. The wind speed is coming there. The wind speed is coming there. Wind speed is coming. There is some the density is here. There is some density is here. Actually, it works as a incompressible flow. Incompressible flow. It's incompressible flow meaning the density is constant. The density is constant, almost constant. This is almost constant. Density is almost constant. It's upstream and downstream. We are calling this upstream and downstream. Here's a downstream. That's upstream and downstream. That is the density is constant. Then here the wind speed, this V1 is a V2. Generally, V1 is higher than V2. Higher than V2. Then here, that's the reason this envelope is becoming larger. Otherwise, it may be accommodate higher volume backside. Higher volume backside. Density is equal. Wind speed is low. Wind speed is low. If we consider similar amount of mass flow in here to there, then we need to accommodate same mass upstream and downstream. Then there is a mass is same. However, this volume need to be increased due to wind speed is low there. Then this type of envelope is developed around the wind rotor. So the wind speed path is becoming there. Then actually we are calling there. That is the incompressible flow, the one. Now, shall we understand some other point here? Now, here is some energy is coming there. Some energy is coming there. It is M. Some energy is coming there. If we need to absorb this all energy, what happens? What do you think? Can somebody, if you absorb this all energy, 100% conversion, if you absorb 100% conversion, what happens? What is the wind speed here?
It should be 0.
If you absorb all energy, what should the wind speed in downstream?
Should be 0.
Should be 0. It cannot be happen, no? Because of if it is 0, there are no any airflow. There are no any airflow. It should be some airflow there. Then in this logic, we can argue that we cannot develop 100% efficient wind turbine. We cannot develop 100% wind turbine. If you want to develop 100% conversion efficiency wind turbine, the downstream wind speed should be 0. It cannot be happen. Then if it is 0, that means no any airflow. That means we need to maintain that V1 and V2 some optimum level. The ratio between V1 to V2 ratio should be optimum level. Then that's the point today I'm going to discuss with you. What should be the optimal ratio in between upstream and downstream for maximum energy extraction? Then now we know that. Then for 100% conversion efficiency, if we need to convert 100% energy, the wind energy to mechanical energy, downstream should be 0 because of all energy need to be converted to mechanical. But it cannot be possible because of that there's open air concept. Then there should be flow there. Yeah. Now that is the now here we can write the equation like that is extracted energy. There's here the kinetic energy in the upstream, kinetic energy downstream here. Then the difference is absorbed by wind rotor. This V1 is upstream in speed, V2 is a downstream speed. Okay. Now we can write this simple equation. It's not much complex one. It's not much complex one. Actually, we are calling ideal performance of wind rotor. Then that is the flow rate equations we can write here. Then we can define the VT. The VT we can define here. That means the wind speed at middle of wind rotor. Then it is a mean value of V1 and V2 upstream and downstream. Then we can take the V1 plus V2 divided by 2. There's a point here. Now we can write down this equation, energy equations. That is my previous equation. Then it is substitute by this one. Actually, this VT is coming there. Then because of VT is the flow rate. The flow rate can be calculated by VT here. That is the VT is coming here. That the flow rate is coming there. Now we can write these equations. We can write this equation because of we don't know VT. VT can be substituted by this equation. It can be substituted there. Now, CP I already explained there. The CP mean here that the input energy and output energy. So input energy is P naught. So output energy by the mechanical energy is P out. Then there's a CP value here. Now, if we substitute like this type of ratio, when we define this ratio, K is equal V to this ratio, then we can write this equation. Then the V1, V2 we can substitute here. Now this can be optimized. How we can do the optimization? This equation generally in the mathematically we are doing optimization, maximum and minima. This is simple by using K. It should be 0. There is maximum or minimum curve. CP is the function of K here. CP is the function of K. CP is the function of K. This is coming there. Now, in this minimization, we can find out this value. In this minimization, we can find out this simple mathematics, maximization or minimization concept. Shall I explain it again? Then this kinetic energy, this kinetic energy concept is the mass. The mass can be expressed by VT and rho. Mass passed to the wind rotor can be expressed by the VT and V rho, because the V is the velocity passed to, the VT is the pass to the wind rotor. If we know the density, we can find out the mass there. Then that is the point here. The rho is coming there. Rho AVT is coming here. Rho AVT is coming there. Now the VT can be substituted by this equation. VTs can be substituted by the mean value of upstream and downstream. Then this equation we can write here. Now, if we define the ratio of the upstream and downstream, K can be defined here. Now, we are calling this a bridge limit. Keep in mind, you should be able to derive bridge limit very clearly. You should be able to derive bridge limit. The bridge limit means maximum possible energy harnessed by a wind rotor. That's the maximum possible wind. Then we cannot go beyond that. We cannot. This is a theoretical one. This is theoretical efficiency. This is a theoretical conversion efficiency by a wind rotor. That is independently number of rotor blades, aerofoil, and nacelle shapes, tip loss, hub loss. Without considering all that, maximum possible conversion efficiency is the 0.593. We are calling this the bridge limit. Then you can see now by wind energy, we cannot absorb all energy. Now that is the optimal ratio. That's the optimal ratio. What I already explained there. Now this is the optimal ratio. The K we can find out here. It's the K value. The K we can find out here. K is the 1/3. The K is the 1/3 is optimal. If we can maintain that ratio, we can harness maximum possible energy. Now our object is how we can maintain that upstream and downstream wind speed ratio to 1/3. Then that's the point here. Then if we cannot maintain that, we cannot harness that energy. We are wasting energy. Then we are talking this thing very in detail in maybe the 3rd semester. How we can maintain that, how we can maintain the maximum possible, how we can absorb maximum possible energy from a wind turbine. Then there's a one point. Actually, we are calling it this limit. There are a lot of these type of limitations in the world. Can you remember? Then I hope you all have the engineering background. The Carnot cycle efficiency, that's also one thermodynamic efficiency. The Carnot cycle efficiency, yes. What is the Carnot cycle efficiency? It's 40%, no? Then there is auto cycle. This auto cycle cannot go beyond 40% conversion efficiency. Any internal combustion engine, we cannot go beyond 40%. Even though any improvement, maybe supercooler, maybe a intercooler, or any concept, we can go beyond 40% one conversion efficiency. The similar like the aerodynamics one, we cannot go beyond that. We cannot go beyond 0.593. There's a maximum possible conversion efficiency. That's the reason is the most of the commercial wind turbine, like the very advanced wind turbine, even though very advanced wind turbines, large wind turbines, the CP value is around 4.2, 4.3, like that. Even though less than that value, they keep in mind that the conversion efficiency of the CP value is given like that. You can check that in any values, because of there are some other losses should be there, the wake loss. We can talk these things with you, why that wake loss is happening. Okay. Do we have any questions? Questions you can raise with me. Okay, no questions, we can go forward. Or shall I ask some questions from you? Yes. Now, this is a mechanical power generated by a rotor. However, now the rotor characteristics like that. The real rotor characteristics is like that. You can see here. Now, actually, the one other parameter I can come with you. What's another parameter? So we are calling that is a tip speed ratio. We are calling this lambda. Lambda is R omega upon V. So R omega means there is R. This rotational speed is omega. Now the tip is moving R omega. R omega. The wind speed is V. Now the tip is moving R omega. Wind speed is V. Now lambda is R omega upon V. That also a very important one. Generally, this is CP. This is the important curve we need to be find out for any wind rotor. Tip speed ratio with CP. You can see here that this tip speed ratio, there are the best tip speed ratio is there. Here there's a 7. At the 7 only it gives 0.4. At 7 only it gives 0.4. What I explained previously, if the tip speed is less than 7, we cannot maintain that 1/3 ratio upstream and downstream. Then that's the point here. Then we need to maintain that the tip speed ratio at 7 to the maintain upstream and downstream wind speed exactly. Then at that point only this wind rotor absorb maximum possible energy from wind. Then actually now we can generate this curve, obviously. Okay, I'll give that homework to in the Moodle. However, the homework, if you know the wind rotor diameter, shall we think our diameter is 126 meter diameter, same as Mana wind park, wind turbine Vestas, that wind turbine 1261. Shall we take this is the, if this is the CP values, say CP values, I hope this recording will upload it. You take that CP values, then you can find out each and every wind speed, what are the curves there. By using Excel sheet, you can do that. Because if you know the rotation speed, now you need to convert that axis. Here is a rotation speed to power output. Rotational speed to power output. CP is the conversion efficiency. Now the power mean with the wind speed, those are the wind speed. Each and every wind speed. You can see each and this is the wind speed 4 meters per second. This is 4 meters per second. Shall I go for the mouse there? This is 4 meters per second, 5 meters per second, 6 meters, 6, 7, 8, 9, 10. That type of changes are there. Now, what happened in the recent, what is happening actually in the real world? The real world, the wind speed is not constant. Real world, the wind speed is varying very quickly. Wind speed is varying very quickly. Now, if the wind speed is varied, shall we think from 6 meters per second to 7 meters per second. Now, the wind, if it is 6 meters per second, here, shall we think? There's a 6 meters per second, wind rotor need to rotate around 35 radians per second. 35. If it is, the wind speed is varying to 7, it should be around 42 radians per second. Now you can understand that with the variation of wind speed, the rotational speed also should be varied. Otherwise, it cannot be harnessed maximum energy. Maximally, there's a main challenging task of the modern wind turbine. Then if you are, otherwise you are wasting your energy. Then you need to waste your energy. Now there are a lot of the topology people are using to tackle that problem. To tackle that problem, we are going to discuss this issue up to some level in this semester too. Now the first homework, you should be able to convert this CP to these curves. Please use your Excel sheet. Just you need this equation and CP equation. The CP is the P naught actually. CP. Okay, I'll write that point here also again. CP is P naught. Here is the wind energy, total wind energy. There is some mechanical energy. There's a mechanical energy. Here is the mechanical energy here. In the y-axis, there's a mechanical energy. Here is the P. Then here, there is half a rho V cube is there. Right? Now we are called this optimum line is coming there. There is optimum line. Need to be optimum. This operation optimum line we can find out for a different wind speed. With a different wind speed, there is optimum line. Now, shall I address this problem here? There's a wind rotor is there. Okay, shall we think wind rotor is coupled with the generator? Wind rotor is coupled with generator. These are the wind rotor curves. These are the wind rotor curves. These are the wind rotor curves. Generator also have some other curve. Generator also have some other torque speed curves. Then we need to comply the rotor curves with generator curves. Then if we can match that generator curve with this optimum line only, we can absorb maximum possible power. Shall we think? Our generator, our machine is operated at constant RPM. Shall we think 400? There is a constant RPM. Shall we think? There's a constant RPM. What happened? At 3 meters per second, it is very, very small power. Like you can see, it cannot be harnessed maximum possible. Maybe even though only 7 meters per second only it can be come to the highest CP values. Other all wind speed, it's become lower and lower. Can you remember if somebody have that? We had our very first pilot plant in Hambantota. It's a 4 megawatt plant. It's a 4 megawatt plant. It installed 600 kilowatts, 5 machines. That's the point. That's the very first the wind park in Sri Lanka. Then these also the Vestas machines. The long time ago. And presently, these all machines are no more operations in Hambantota. They all removed due to many reasons. This all ready. These are the constant RPM machines. These are the, I think the true set of RPM. However, we are calling constant RPM machines. At that time, it was like that way. These wind turbines were work like in the similar way. Then only the one wind speed only it can be harness maximum possible energy. Other all point it not work at low efficiency. Then we will discuss these things later very clearly. Some points need to be addressed. You should understand here. The wind rotor curves should be comply with generator curves. Generator curves will have different because they are only one line. There's a load curve. There's a load curve of generator. Now, other one is that for a wind energy conversions things. No, can one student can give answer? The most of the wind turbine in for a energy generation, we are using 3-bladed wind turbine. What's the reason that?
It has a higher base constant. It has a higher CP.
Higher CP, okay. One other answer, some other student?
Is it
3P.
considering the stability?
Yes, good. There's one stability also, another point is there.
To get the higher efficiency,
Little bit louder.
to get higher efficiency,
Yes, that's also a good point. High efficiency, stability. Yes. How it's become high efficiency? High efficiency. Why? What's the reason? Okay, I'll explain that. Efficiency. That means you can see now we know that the linear momentum. Actually, we use the linear momentum theory to explain that Bliss limit. That's the point here. Now the conversion one. Then however, there are some wake also generated. The wake also generated. Wake also generated behind the rotor. The wake is equal the torque on top of the wind rotor. The torque. Actually, resultant the torque. The resultant force is act as a wake there because of the general wake is generating in the rotational side like that. Shall I? The blade is here. I shall write the blade here. Blade is moved to in direction. This is a part. This is a part. The blade is moved to that direction. Then is a forces. The forces apply here. Then in the opposite side, on top of the wind, there are some other forces apply there to wind. Then that force make a wake here. The wake here. That means opposite direction. There's an opposite force on top of the wind is make a wake there. Then now the wake is generated. The wake is lost. The wake is lost because linear. There's a linear momentum is the real energy extraction. Yeah, the wake motion. Actually, then we are considering the V1 and V2. V2 is a linear motion. Actually, above all that previous theory, we consider only horizontal component only. That not yes. Actually, we consider only horizontal component. but there are some energy in the wake also there, the wake energy also there. This is the loss here because of this input energy, output energy. Difference between input and output is converted to mechanical energy. We are not encountered that due to wake, the wake that means rotational. Actually we are calling them wake there. Now what is happening? If the number of blade is high, it generates more wake. Then if the number of blades are low, the wake is less. It's go very high RPM. High RPM, lower. There's a high RPM, low torque. Energy. I think this energy is equal torque into. This is a common equation. We know that. Everybody know that. Energy is equal torque into rotational speed. Same energy, if we can increase torque, we can lower it rotational speed. If the number of blades are low, it's a high RPM, low torque. If the number of blades is high torque, low RPM. Shall we think same energy? However, that conversion efficiency, the wake loss is the point there. Then that's the reason what I need to explain of this point. There are many type of wind turbines are there. There are many type of wind turbines. Single-bladed wind turbines also people are used some places. Two-bladed. Did you see two-bladed wind turbine in somewhere? Two-bladed wind turbines. One student. Maybe small wind turbines. Surely. Did you see very small scale wind turbine, two-bladed one? Nobody. Yes, actually some small scale wind turbine manufacturer, they are using two-bladed small scale wind turbines because of it can be very high RPM, then it can be very much quickly comply with the generator without any gearbox and everything. There are some other disadvantages there. I can explain that now. Now you can see a single blade one is the highest efficiency. This is highest efficiency. This is low efficiency. Multiplied the low efficiency, high because this wake loss is very low. Here is the wake loss is very low. If you have any questions, I can explain it again, no problem. You can ask. Here the low wake loss, high efficiency, high wake loss, low efficiency. Now, why people are using three-bladed one? Yes, the stability, yes, the balancing and everything. Three-bladed are the most commonly configuration. With the mechanically, we can find out the optimum configurations. That's the reason because it's a yaw-in comfortability. It's yaw-in. I'll explain that at the point of yaw-in there. At the point of yaw-in, the three-bladed one is very comfortable. That's the reason three-bladed concept is people are using there. Now, keep in mind that generally three-bladed wind turbines are that is the lambda. Lambda is people are using around maybe 5 to 8. Check that all large-scale wind turbine, all large-scale three-bladed wind turbines, lambda is in between that 5 to generally 7, 8, like that range. We have speed ratio is a very important parameter for any wind turbines because the CP is given with respect to lambda there. Then the why we are using this multi-bladed wind turbine, you can see, I explained that because of energy is equal torque into RPM. It is high torque is there where we require the high torque applications. High torque application, we require multi-blade. The mechanical device. If we need to drive the mechanical forces, obviously we require the high torque. Maybe a water pump, a grinding floor, any places. Then for electrical generations, we are using most commonly three-blade or some small scale we are using two-blade. Single blade may be very seldomly used due to the unbalances, so vibrations and everything is coming there due to that reason only. Otherwise, single blade one is the highest efficient wind turbine in the world. See, single blade wind turbine is the highest efficient wind turbine in in the world. The reason is that low wake loss. There are some chat in the chat box. I did notice that. Please, I'll try to what the students say. Right, then the previous questions to change. This question I couldn't understand. It is possible to change the horizontal axis of wind turbine. Can little bit explain? No, can you switch on your mic and you can say that that question is not clear to me. Nalin,
Okay, sir. Is it possible to change the axis? Mean the wind, if you say that wind is flowing from north to south, so we can get the maximum efficiency by changing the axis of the horizontal axis of the wind turbine into the north side. So that is it possible to change? Mean it is possible to rotate the blade axis, that's mean horizontal axis.
yes. That is very good. That is very good questions. Actually, we are calling yaw wind. The yaw wind is the concept here. Yaw mean we can orient wind rotor to proper direction. Generally, all wind turbines, all horizontal axis wind turbine, the yaw wind techniques are there. The yaw wind concept is there. For large wind turbines, okay, so shall I start with large wind turbines? In the large wind turbines, they have the wind sensor on top of that in the that been orient to proper direction time to time. I think, is it your question, Nali?
In middle part, I think we didn't hear anything. I think some.
Yeah, sorry. Then there's a top part of the large wind turbine. Then the wind rotor and nacelle. Generally, it can be rotate. It can rotate to orient to wind direction. Orient to wind direction. We are calling this yaw wind, the yaw wind action. The yaw wind is doing for large wind turbines. That is doing time to time. That means within some time period, maybe 5 minutes time, 10 minutes time, that depend on the manufacturer. After detecting proper wind direction, wind turbine is yaw to proper wind direction. Because of are there any misalignment is there? All energy cannot be absorbed by a wind rotor. It should be accurately oriented to the correct wind direction. At that point only, it can be absorbed, all energy coming from the wind. Right?
Okay, thank you, sir.
Right. But in the small wind turbine, maybe it has a rudder there. The rudder is, we are calling active control. Yes. Then automatically small scale wind turbine is oriented to the wind direction. Due to that, the rudder. You can see in this one, in this picture, this is the multi-bladed wind turbine. It has a rudder there. It's the backside. This rudder is oriented to the proper direction of the wind turbine. But for a large wind turbine, it cannot be possible because of large masses in top of the rudder cannot be used for because of due to some other reason, because of the rotating mass. Large rotating mass cannot be rotate. That means yaw wind quickly due to it has a large moment of inertia. Then there's a reason, there's a common reason the two-bladed wind turbines are not using for a large-scale wind turbines. There's one example. If the wind rotor in this direction, shall you think it's a two-bladed one? Then it is a wind rotor in this direction. Then it's a tower axis in this direction. Then the moment of inertia and the rotor is very, very high. The axis of there, then it cannot be rotate in that direction because of the high moment of inertia. In the wind rotor is in this direction, is very low moment of inertia. Then it can be very easily rotate. Then you can see in the rotating mass, the moment of inertia around the tower axis is quickly varied. Due to that reason, large two-bladed wind rotors, wind turbines cannot be yaw. That's the main reason that for a large scale wind turbines, two-bladed wind turbine rotors are not using. That's the first one is the yawing problem. Second one is the balancing problem. That's the reason, that's the main reason people are using three-bladed one. Two-bladed wind rotors, large wind rotors cannot be yawing because of that issue. The rotating mass, moment of inertia, variation, the orientation of the wind rotor, the vertical position and the horizontal position. Okay, we can discuss these things quickly. Actually, yawing concept is in maybe in my next few slides are there. Then as the main features, I'm not going to discuss these things. I already discussed this in semester 1. Then actually, this is the point, maybe Nalim's question here. Wind rotor can be yaw like that. Actually, we are calling this yawing. Yawing is here generally. This wind rotor can be yaw. Yawing. This yawing is doing by detecting wind direction. There's a sensor on top of that. There's a sensor here. Generally, sensor here. There's a wind vane there. If you very clearly closely look upon that, some modern turbines use different technology. Not only that wind vane, there are different high technology people are using there. Sometimes maybe the torque and unbalanced things. A lot of techniques are using to predict wind direction. We are calling prediction. There are a lot of algorithms are using to predict wind direction. Okay, shall we think very simply? It has some wind sensor, direction sensor. Then by using the direction sensor, by using wind yaw motors, we are calling yaw motors. All top portion is rotated to proper wind direction, the orient to wind direction. We are calling this yaw mechanism. That is yaw mechanism. Now, this is the thing that I need to explain a little bit again here. You can see here the very two-bladed one is rotate very fast compared to three-bladed one, high speed. Then low, this is single-bladed one is the high speed, maybe noise also high. Some of the issues are there. There's a unbalancing issues are there, both the two-bladed and single-blade. But these two are this is highest efficient wind turbine. People are not, even though people are not using. Even though people are not using due to some mechanical reason. Theoretically, it is highest one. Okay. Now the topology. Some topology need to be discussed with you. Topology need to be discussed with you. Yes, I need to manage the time now. We have only 10 minutes more. Quickly, I'll go with the topology and okay, we can discuss these things in detail in semester 3 if you select wind energy. Shall I share that? Yes. This is one configuration here. See here now. There is the power flow concept. It's a power flow concept. You can find out. Actually, this is permanent magnet generators. Some modern wind turbines are using the multipole generators. No problem. It's maybe other synchronous type or other type of generators can be used here. there are the few type of configurations are there. We can see the 4 type of configurations we can see. Danish concept. Actually, this Danish concept presently people are not using. This Danish concept people are not presently not using because of, actually this is the concept we were using the Hambam Tota Park long time ago. These induction machines are there. That is constant speed because of the generator is coupled with the grid directly, is governed by grid. With there's a rotational speed of a generator is governed with the grid frequency at a constant RPM. Then the rotor also rotate at constant RPM. Maybe you are not, maybe not, you are noticed that there's a hum pump to the wind turbine. Did you see that hum pump to the wind turbine? Some student, maybe a few years back, 5 years, 10 years back. Did you see hum pump? Professionally no more there. Any student? Did you see that hum pump to the wind park for 5 megawatt plant? Nobody?
So is it the one which is by the SOAR, the facility? The SOAR
Lot.
production facility?
Yes, that is now near the harbor now. Now the presently there are no wind turbine. Hambam Tota, Mirijavila. Did you see that previously? Long time ago, maybe 5, 10 years back. Nobody. Okay, no problem. Then maybe if you didn't notice that this wind turbines are, even though any wind speed, it rotate constant RPM. Actually, now the Mana wind turbines, it changed its RPM, but maybe the large diameter we cannot observe very clearly. However, it changed its RPM with respect to the wind speed also. The Danish type wind turbine, the concept is previously used very less efficiency, but a low cost wind turbine. The people used long time ago, developed that that time, maybe the very first year. Now later on that also developed a little bit due to overcome that issue, the comply with the rotor curves, generator curves, using some resistance bank, then the variable resistance, it changed the RPM a little bit to comply with that. Now, these two are the most commonly used the present systems. The propulsion system. Now the defect one, we are going to talk in detail. There's a generator have stator and rotor. There are two winding systems are there. There's a rotor winding and stator windings. Then RPM, the generator rotational speed is depend on stator and rotor frequency. Then here in this case, we can change stator frequency. That means stator frequency by using converter. It's a frequency converter. By using frequency converter. Now this rotational speed can be varied, comply with variation of wind speed. That's defect one. Here there's a the full converter one. Here it can be permanent magnet or synchronous generator. There's a frequency converter is there. Total frequency converter is there. That means here the frequency in the generator side and the grid side is not equal. That is depend on this optimum working condition can be operating. So now the modern wind turbine people are using this technology, the full converter technology, due to with recent power electronics improvements, the full converter concept is they are using. Now these two things I'm going to discuss with you very in detail, the concept and everything. Maybe maybe both mechanical, electrical controls and everything. No, not only because of the wind engineering is a multidisciplinary one, not only one area. Electrical, mechanical both should be there. Otherwise, we cannot understand these things. Then both need to be learned together. Then in the technical things, I little bit go quickly. I'm not going to discuss these things today because of not sufficient time now. Shall we go to quickly one of our case studies? Now we are calling this the power curve of a wind turbine. that was a very important point here. Power curve of wind turbine, typical power curve. Here, this point is important cut in wind speed. The cut in wind speed means this is the wind speed variation, this is a power generation. This is a power generation. Then with the variation of wind speed, how the power is varied. The cut in wind speed is where that the wind turbine is start to generate power. We are calling cut in wind speed. This is 3 meters per second. At the 3 meters per second only, it start to generate power. Up to 3 meters per second, it not generate any power. You can see here. Then, however, this rated wind speed is coming there. The rated wind is rated power. This power controlling is coming here. Even though any high wind speed is not generate, it's keep constant power. That means the efficiency is high. This point generally is go the less efficiency because of the power controlling is happening is after that point. In this point the power in this range power controlling happening. In this range, maximum power point controlling is operating because of we need to operate. Most of the time, wind turbine is operating in this region. Then this is power control region. Right. Shall we talk about that? This is the point I already explained with you. One case study. Yes, okay, again, this is the graph here. One case study. Shall little bit talk about our Mana wind turbine because of this is the actually the case study of there are many wind park around Sri Lanka. There are many private parties are developed near the Butlam region as well as the Jaffna zone near the Chunakam, the Parantan region, the Punale and everything. There are a lot of the private parties are developed there. However, this is the wind park is belong to the Ceylon Mills Board. And it's a Vestas 126, I think. So not it's a 126 3.5 meg. I think the diameter is a 126 maybe there. Yes, Stamba only one. I hope there are 33 wind turbines installed at that place. I can say that this is the largest wind turbine type in South Asia, even though I hope in the last few years there are no this much of large wind turbine we couldn't observe even though India also. This is 3.45 megawatt, the largest one. Because India have some other restrictions. They have other restrictions due to because they need to their local contributions. This is good actually in the commercial wise. They need to do their local contributions. That's the reason they are not going to large wind turbines. But fortunately, we have 3.45 megawatt wind turbines. Even though in the maybe stage 2 we can go higher, much more higher one, maybe 5 or 6 megawatt one. Then this is a Mana Park here. Some pictures in Mana Park, maybe 87 meters the tower height. Then those are as a case study. You can see this is a Vestas that machine. The power curve is there. You can see here is a power curve. Observe the power with that point. That is starting point with 3 meter per second. Rated is around 11 meter per second. That is almost comply with that regional wind speeds there. Then we can discuss later on what are the environmental issues and everything later on if you like, no problem. However, I think those are the layout of wind turbine. There as well as this generalize the wind climate by developed by WASFOP that the same park. The 33 wind turbines, wind rows, and all that the predicted values also there. Hope if you have any questions, you can ask now. We can spend a few more minutes with your interest, no problem. Do any student has any questions regarding this area, even though other?
I have one question.
Yes, please.
We build offshore wind plants. Why is the wind speed higher in the sea?
Wind speed higher in the sea. Yes. Somewhat good questions. If you go to the, shall I go to the wind atlas very quickly? The reason is that geographical, actually reason is, there are two reasons are there. The one reason is the ground roughness, very low. Other one is, shall I, rather than go to the, if you couldn't understand that, please tell me. Then rather than in the Sri Lankan situations, please wait. Actually, in the Sri Lankan, that's what I need to. Actually, in a Sri Lankan situation like that, Sri Lanka is like that, no? India is like that. There's a mountain is there. Actually, we are facing a lot of monsoon wind. The wind is coming from, as well as wind is coming from there. In general, due to that mountain, this wind is directed like that. Actually, we can go for that the previous slide, what are the real situation. And that's the reason that there are no any wind potential in these two places. So there's a wind tunnel is coming there. Actually, this almost, that's the reason this Kanyakumari and this India, these places, a large amount of wind potential is there. That's the reason this Mana also very good wind potential. Here, so we can identify these two places. These two places are the most possible places for offshore wind turbine. This is due to that wind tunneling effect, as well as the ground roughness also very much low. I think maybe the recent surveys are going on to develop some wind park in these two places, the offshore wind turbine. If you go to the wind atlas, it's very clearly observed that then the wind tunneling is happening at this point. There's a point in India also try to harness some wind energy in these places. There are a lot of wind turbines in these places. And there's a Hambantota also we can see here. Then due to that mountain, Pithutlagal mountain is diverted. Then that's the reason Colombo and Batiklo, and there are no any wind potential. Colombo and Batiklo, there are no any wind potential. Then even though there are some wind potential in the top of the mountain, then Bevala and this area, again, there's a wind is going up, and the uppermost places, the high level, high mountains, we have wind. But unfortunately, we cannot harness that due to the land restrictions as well as the turbine installation issues. Can you understand? Did you got the point? Is it your answer for your question?
Yeah, I got it. Yes, thanks.
Right.
So I have a question. What is the minimum distance we have to maintain between two wind plants?
Then shall we think like this type of one? Then it's the wind is coming there. Okay, now the wind turbine is like here. If it is better to maintain 5 to 7 diameter here, then here generally 10 diameter. That depends on your plant factor, however. Like that, then if you like that, then that is thumb rule. Generally, the 5 to 7 diameter. Like the Mana also, we are maintaining 5D, I think so. 5D maybe. The Mana also 5D. I need to check that. 5 to 7 diameter, maybe because of that is the diameter of wind turbine. 5 to 7, there's a 10 diameter. This is parallel row. The wind is the prevailing row. The wind is coming here. This is a 5D. And then are there any row backward? The backside that is 10D. However, that can be changed if we go for the maybe your cost of generations. Sometime in the cost of generations, maybe you may require higher amount of wind energy. You can reduce that. You can compromise your plant factor. You can absorb more energy. Then if you reduce that the spacing, you can generate more energy, but you can sacrifice your plant factor. Then you have to think about that cost of energy generation. That may analyze cost of energy. There's a thumb rule. However, in detail finance assessment need to be do for a microsite in level. What is the distance between all those two? The micrositing is the concept behind there. We have the software like bus, like this type of software we can use. The wake and everything can be analyzed. Okay.
So, okay, sir. Then in your answer, I think given in the X and Y direction. So how about the Z axis?
Z axis mean? What do you mean? Z axis mean height, no?
Yeah, yeah.
Ah.
Then that is a when we consider the wind plant in the height of same alignment. So then it
Same
will be
line.
possible to- yeah, it will be possible
Same
to
line.
use height.
Same line. You are using the same line. They should be same height. Should be there. It's better. If you go for a back row, maybe your height maybe can be increased. If the wind is coming in this direction most of the time, I think you can use that type of concept. Shall you think about manna? The manna, the most of the time it comes the north, west, no? Then the second row, you can increase the height. Then it can be harness more energy. But if the wind is coming that direction, it is vice versa. That becomes worse. Actually, in the manna, then you have received the both. Like that's the reason the wind right is there. Shall we think this park is come to CEB? CEB. Okay, CEB. Now this park is going to some Indian company, Adani. Then they are going to install higher tower height wind turbines. Then it will affect to the CEB wind turbines. Then there's a wind right need to be, we need to discuss in very detail in this wind right. Then some rule need to be followed. Then the second owner need to be addressed. Then if after installation of the second wind park, it will affect to the first wind park. Then there are some rules are there. You cannot increase the wind height, wind rotor height. Obviously, if you use the higher wind tower height, it can be absorb more energy because a wake is not affected to that one. Actually, the proper micrositing need to be do that. Otherwise, we cannot say exactly because of these things. That's depend on the wind turbine types also. The thrust curve and everything need to be analyzed very in detail. Okay.
Okay, thank you, sir.
Question? If you have not any question, I can wind up. Okay, in time also, we already passed the time. No problem. If you have any questions, please email me. Or I think the thing is that please follow that Learnify modules. There are possibility to write your questions as well as take feedback. Then actually, I would like to use that platform. Please, it's open-ended questions. You can write your open-ended questions. Then as a platform, you can use as your colleagues other feedback also. Use that platform very proper way, maybe useful to you. Then I also join with that platform time to time. Please use that, ask this question through that Learnify platform. Okay, thank you very much. Shall I wind up the session?
Okay, sir.
Okay, thank you.
Thank you, sir.
Thank you, sir. Good night.